Hello. The exercise that you have just completed should have given you a result something like this. In that exercises, you calculated two distinct estimators for the average volume of the bubbles. Furthermore, you repeated this experiment multiple times. The results for your various experiments are shown in blue and red on this slide. What you can see clearly is that the blue results appear to be markedly different from the red results. This is not simply in the sense that one of these estimators is more precise than the other. If I show the centres of these distributions of blue and red points, you can see that the centres are in completely different places. In fact, all of the blue points have a value that is larger than the value of the red points. To understand what is going wrong here, let's first consider what we are calculating. When we calculated the blue points, we calculated the average volume by first cubing the radius of the bubbles, and only after we had finished that process of cubing did we average. To calculate the red points, by contrast, we first calculated the average radius by doing the sum shown in the brackets, and only then did we calculate the volume. In other words, the red point is an estimate of the average volume that we get based on the average radius. Importantly, we do not understand what the true expectation is in this case, so we cannot say which of these two estimates that we've obtained is more accurate. The fact that the two estimates are not centered on the same value, however, clearly indicates that one or both of these estimates of the average volume is inaccurate. It is not simply that one of these estimators is more precise than the other, as we have seen before. One or both of these estimators of the average volume of the bubbles is giving us an answer that is wrong. To understand what is going wrong, it is useful to introduce the following expression for the estimate we get when we calculate a sample mean. In this expression, x bar is the sample mean, and this is written in terms of the true expectation for the random variable capital X. This true expectation is a fixed number, i.e., it is not random. To account for the fact that any estimate of x bar we get by sampling a random variable is random, we thus add to the expectation of x a new random variable called delta. This random variable has an expectation of 0, and it can be positive or negative. We can understand this expression pictorially using the diagram shown here. The horizontal line here is the set of real numbers, and the vertical line indicates the position of the true expectation for the random variable, which, remember, is fixed. When we generate a sample mean, the blue circle, it will be close to the true expectation, but not exactly equal to it. The difference between the true value for the expectation and this estimate of the sample mean is then delta. Remember, though, that the sample mean is a random variable. The blue dot can thus appear in multiple places along the real number line. In these cases, delta will have a different value, which may, as it is in this case, even be negative. Let's thus consider what happens when we insert the fact that the radius is a random variable by using this expression into our equation for the volume of a bubble, 4/3 pi r cubed. Inserting the expression from the previous slide into this equation gives the following, where the randomness in r is now accounted for by the random variable delta. We can expand out the bracket here to obtain the following. We now apply the expectation operator to calculate the expectation of this expression, and to thus make it no longer random. If we remember that expectation is a linear operator, we can bring the expectation operator inside the bracket and then take all of the constants outside the operator and arrive at the following expression. Critically, remember that delta is the only random variable in this expression. Everything else is a scalar and can thus be brought outside the expectation operator. Now notice that we said delta has an expectation of 0. This term that is multiplied by the expectation of delta is thus 0. By a similar token, the final expectation of delta cubed here is also 0. Critically, however, this term is non-zero. Delta is always a real number, and thus delta squared is non-negative. The expectation of delta squared is thus a positive number. What we have thus found, then, is that interrogating the distribution of volumes by transforming the radii in this way is problematic, as the amount of randomness in the distribution for the radii affects our final estimate of the average volume. We say that the estimate of the average volume that is computed from the radii is biased. This thus accounts for the inaccuracies we obtain in our estimates of the average volume. To summarize then, and to return to one of the themes that was highlighted in my introductory video, what we have seen by doing this little numerical experiment is a manifestation of the inequality that is shown at the top of this slide. In general, if we calculate a function g of an expectation, we do not get the same value as the expectation of the function of the random variable. This inequality is only not true if the function g is linear. For every other type of function, we have to carefully check if the quantity on the right of the inequality is a biased estimator for the function of the expectation, in the way that I have just explained. To check for bias, we express our random variable using the equation shown at the bottom of the slide. Here I have written the random variable as a sample mean, but this can be a sample mean calculated from a single random variable, capital X. For most types of random variables, capital X, we can write them as the sum of the true expectation for the random variable, capital X, which remember is a fixed constant, and a random variable, delta. This random variable, delta, has an expectation of 0, and it can be positive or negative. To determine if an estimator for an expectation of a function is biased, we insert this sum of terms into our function g. We then expand out the function using the usual rules of algebra, and until we get a sum of terms. We then exploit the linearity of the expectation operator and look for terms that include the expectation of delta raised to even powers. It is this sequence of steps that we need to use when we consider if the method of moments is an appropriate way to estimate the parameters of random variables. If we find that the resulting expressions are biased, then the method should not be used to estimate the parameter. I hope that is reasonably clear. In the quiz that follows this exercise, You will have a series of opportunities to test your understanding of this technique for detecting whether estimators of functions of expectations are biased or not. Good luck with those exercises, and thanks for your attention.